Okay, welcome to class, everybody. We finished all of our new content, all the new material last class. So today we're going to hold a review. The TAs have yet to tell me if they're going to do a review. Christian, you want to make a quick announcement or you want to wait? So tomorrow night, 5 to 7, Christian's going to be a good man and do that for you. So if you want to come, you're not going to record that though, so we can't record that one. So just come if you want to make it. That said, we will go over stuff today. Before we start the final exam study session today, let me just make a quick note about the clickers. If you're still making up clicker points, here's where we ended. We ended with right around 100 points. So I'm going to say that 100% is if you got 75 points, right? So if you got 3 out of 4, you'll get 100%. Remember, you can make up to 50% of missing points, right? So this means basically everybody should be able to get all 10 out of 10 clicker points towards their final grade. But if you're going to sign up for that, we need you to sign up no later than tonight. I don't want to keep on monitoring that thread. So do the math, figure out how many you need to do. I'll check it one more time tonight. And then you have until December 15th. That's after the final. It's about 3 days after. I don't want to wait much longer than that because I'm going to need that to figure out your final grades, and I want you guys to have your grades posted as soon as possible. John?
If we help out with that, will there be extra points added on if we have like 100% already? Will there be more points added on?
The only one that you'll get extra for is the one that you'll do for extra credit on your homework, for basically to make up for missing homework. Beyond that, we won't do. Unless you just think it's awesome and you want to help out and help us get this thing published. It's going to be cool research. I don't know if I can still send messages to the class, but when we get it published, I'll see if it's possible to make you guys available of the publication. Okay, that said, let's dive into the final review. I posted the study guide. The TAs have the test. They looked at it yesterday with me. Now they're taking it at some point. They haven't finished taking it, so it might get changed a little bit. We might cut some things, add some things, just depending on their feedback. But the test is exactly what you're looking at right here. I literally go from top to bottom, beginning to end. This is every single thing that I expect you to know something about on the test. The test is 2 hours long. It has, instead of the 3 questions like normal, which typically have 3 parts, now we have 5 questions, and they have maybe 4 parts apiece. So it's similar pacing you're going to have to be faced with. It's going to be, you need to work quickly. Arthur? I don't think we're going to post a practice final. I don't think it's helpful because what I'd like you to study is exactly these things. And when we post a practice final, it's inevitably going to have stuff that's not on the study guide, which I think people spend their time studying on rather than the study guide. So I think that you're better off looking here what any of these topics are, finding the homework question that was associated with this, making sure you can do that. I think that's probably a better use of your time. Yeah?
Since you know everything, could you maybe even put like which homework it's associated to?
I don't think I'll do that, just because that would take a lot of time. Yeah. Nick?
How many sheets of notes?
Good question. For the final, this is our 4th exam. If you want to bring 4 sheets of paper, that's great. They don't have to be the 3 from previously. However you want to organize it. Again, my point is not to make you guys memorize stuff. I just want you to organize your thoughts, and getting on 4 sheets means that you won't be scrambling that much through pages and pages of notes. So you got 4 sheets, front and back if you want, print it if you want, I don't care. You can put example problems, you can put old test solutions or homework solutions, I don't care. Anything that helps you do it. Yeah, Rob?
Plus periodic table.
You can also bring a periodic table. I think you might want a periodic table on this one. Again, we'll usually put the information you need on the test, but I think bringing a periodic table would be a good idea. Other questions on the generally speaking? Yeah, Mohammed?
Are we allowed to have all the previous sheets?
If you want to bring those, that's fine, but you can only have 4 sheets total. So whatever you choose for that is fine by me. Yeah.
So is the test fully cumulative, or is it just the thing from the study guide? Is that all that?
So when we made the test, we wanted it to be cumulative, but we covered just so much in this class, right? I mean, exasperated nodding going on everywhere, right? We've covered a ton, and I've only got 6 questions that I could ask about, and then we merged 2 of those questions into one. So there's just no way that I could really cover everything. So we're going to test less on things that you've already seen. So if you look back on previous tests, they're not going to be as useful to you to study as homeworks because I only have so much time I can test you on. So I'm going to try and test mostly on concepts we haven't seen yet that I think are important, and those are the things that are listed right here. Other questions, generally speaking, or should we dive into some of these? Okay, well, what of these would you like, a review of? Yeah, Brendan, go ahead.
Go over just power over time really quick. Since we didn't know about
Go over what one more time?
power over time.
Power over time. I think we've modified this actually. I think I wrote this review and then I changed this, but let's go over it a little bit anyways. Power. Sorry, I'm blind here. Okay, power work time relationship. So all we wanted you to know here is that power is equal to IV. Caps lock is on. Power is equal to the current times the voltage. Power is also equal to what? I squared R, where R is your total resistance, not your resistivity. It's also equal to the energy, right? Let's see, this is divided by time, right? Total energy divided by time. I think that you won't need to memorize those. I think I've modified that question since I wrote that little bit. But this is basic high school physics stuff that you would have seen at some point. Okay, other questions? Everyone good on Fick's second law for thermal transport? Do we want to at least see this thing written out? So again, Fick's second law, that's the one where it's changing with respect to time. It's not under steady state conditions, it's non-steady state condition. So it might be something like the temperature at position X minus the temperature some far distance away from where it's changing is going to be divided by the temperature at the surface minus the temperature far away from where it's changing. That's equal to 1 minus the error function of x, the distance at which tx is being evaluated, divided by 2 square root of alpha t, where alpha now is our thermal diffusivity, which normally we say that thermal conductivity is equal to thermal diffusivity times density times heat capacity. So we've solved for alpha, and that's what you plug in there. It has the units of length squared per second, typically millimeters squared per second, which means if you want this thing to work out, everywhere inside this error function needs to be with no units at the end. It needs to all divide out. So if your x is in meters, then you better make sure that your alpha, your thermal diffusivity, is in meters squared per second. If this is in millimeters squared per second, then you're going to be solving for x in millimeters. And since this is per second, time needs to be in seconds as well in order to make that cancel out. Any questions on using this? Obviously, we've used this in this class to go either up or down in temperature. So if you took an object and you put it in like a warm bath, then we're saying that the temperature of the object, T naught, is what it is. The surface temperature could be warmer, though, than the object, or it could also be colder, right? It could also be colder. Okay. We're going to use the same solution either way. Any questions on this, Takar?
Oh, no, not on this.
Oh, something else?
On your midterm review, is there a section of Miller indices?
Nope. We didn't get to it. And honestly, there's more important stuff. So I'd rather you study other stuff. Rosa?
What is that K equals alpha plus
Okay, good question. This stuff, kappa is thermal conductivity. Rho is density. C sub P, that's heat capacity at constant pressure. Sorry, this is getting crowded. Right? And then alpha is our thermal diffusivity. Okay, other questions I can answer? Yeah, Arthur?
The alpha is different for another scenario, right? Where you ask that.
Yeah, if we're doing fixed second law, instead of for heat moving through a material, if we were then modeling mass moving through a material via diffusion, then we can't use the thermal diffusivity in the error function. We have to use the diffusion coefficient. It has the same units, but it's capital D, and right, it's a different value. Okay, same units, different value. Other questions? Yes, Thomas?
Thermal conductivity, is that tabulated in the chart or something?
Well, lots and lots of ways we could ask you this question. Thermal conductivity is the hardest of all these things to measure, for sure. Thermal conductivity is. I think we mentioned it, but when you try and measure thermal conductivity, what you run into is like, let's say that you've got a bar and you're going to pass heat through it. It seems like it would be simple to measure thermal conductivity because you could just say that Q from Fick's first law under steady state conditions is equal to negative thermal conductivity dt dx. So you're like, oh, this is easy. All we have to do is like put a thermoprobe here, put a thermoprobe there, so you know what temperature 1 is and temperature 2 is. You know the separation distance, so you know what x is. So you've got dt dx, and you say that sounds pretty great. What's hard is it's hard to know how much flux of heat is going through it because you end up losing heat out the sides radiatively, right? Just like if you heat something up and it starts to turn orange, it's giving heat off the sides. So it's really hard to know how much heat is going through your sample. So thermal conductivity is actually the hardest of these things to measure. So instead, what they do is they measure these three things. Heat capacities, it sucks to measure, but it's not like it's that hard. It just takes forever. Density is easy. Thermal diffusivity is not that hard to measure. It's easier than thermal conductivity. There's less error involved. Other questions I can answer? Yeah. Yeah, we can move on.
Yeah, so calculating critical nuclear radius and nuclear energy.
Okay.
So there's the equation for when it's I think it was when it's spherical, but you said that's the only one we're going to need, right?
Yeah, on the homework, I think I had to do it for a cube or something. I don't remember. On the midterm, I'm not going to make you use anything for a cube or octahedron or anything weird like that. You're just going to use the sphere. So you do need to know it for a sphere. So let's remind ourselves what that was. That was in chapter 11 on kinetics. And if you go to, it's right here. So this was for a sphere, right? These two equations. You've got these two ones here. Right. Again, those are for spherical nuclei forming upon supercooling. These are for, let's see, this is for the homogeneous case. If it was heterogeneous, how would it look different? Would they both look different? Would one of them look different? What would be different? Yeah, R star is not changed, but delta G star would be modified to include what? It would have a number here, basically. We call it S. S is a function of the wetting angle, right? And that's a number between 0 and 1, right? And so basically it takes whatever your homogeneous value is right there, and it can only reduce it. It could reduce it drastically if that number is close to 0, or not very much if it's close to 1. That's the difference between homogeneous and heterogeneous.
How do we find that number?
We find that number with this one in the notes. So in the notes we talked about this as, go down and find it. I think it's above it. It's right, did I pass it? Maybe it's below this, let's find it. Okay, right here. That's your expression, is this guy. So it's in the notes that S of theta, it depends on the wetting angle theta, and that's all, right? It's a bunch of trigonometric functions. And really, if you remember what we talked about, is what this expression here is it's basically telling you how to account for the cap of a sphere rather than the entire sphere, right? Because the wetting angle is now no longer a perfect droplet on your material. It's something less than a perfect droplet. And so you don't need to take into account the volume to surface area ratio of a whole sphere. You only need that ratio for the cap of a sphere. And that's what S of theta is doing. Okay? Other questions I can answer? Yeah. And on all these questions, if the only thing I'll expect you to know is basic stuff, like you guys know when water boils and melts. You guys, like what else would you expect? I'd expect you to know basically nothing, right? I'd have to give it to you. Like you don't know what temperature it's not that you guys don't know nothing, right? But anything else I'd have to give you, right? Yeah.
What about the specific heat capacity of water?
Specific heat, you might remember that. I would give you that. It's what, 4.8 or 1 or something. So basic stuff I'll expect you to know the density of water. I don't know. Basic things you ought to know. right? Go ahead, Rosa.
Can we do a factorization of n star?
N star, yeah, let's do that. So I think R star and delta G star are straightforward. Any last questions before we leave this? Everything, you know what to use everywhere here?
Can you show that equation, that heterogeneous equation, just for a couple more seconds?
Yeah, let me actually grab it and I'll drop it over here. Right here. So if you need it, that's how you calculate the difference between the activation of homogeneous and heterogeneous. You just apply this term to the end of it, where theta is your wetting angle. Spencer, or do you have a question about the Spencer or something else?
Yeah, what was the delta HF again?
Okay, delta HF, that's your enthalpy of fusion. So again, going back to chemistry, this is the, let's say you've got a pot of water that you want to boil. You heat it up and you're pouring heat into the system up until it reaches 100 degrees Celsius. At that point, heat is still going into the system, but the temperature's not changing. So the way that we understand what's happening there is we know that there's an energy involved with the phase change itself. Basically, to break those water molecules up and turn them into a gas, it has to absorb some energy. That's this enthalpy of fusion, right? That's what we're talking about. In the case, that's for going from liquid to vapor, but there's a similar enthalpy involved with the transformation from liquid to solid, solid to liquid, right? So that's what this is talking about. Since we've in this class been talking about starting in the liquid phase and forming a solid, this would be the heat involved in that transformation. That's something that I would give you. The surface energy is something I would give you. You guys don't have, maybe you could ballpark those, but I'm not going to expect you to. I'll give you numbers for these things. Okay? And then T alpha beta, that's the temperature at which the transformation should occur if you're looking at a phase diagram. And again, a phase diagram tells you thermodynamically speaking where things ought to occur. And in the real world, we don't hit that. We can overcool things, we can supercool things, because there's this kinetic constraint which comes from surface area and the energy penalty associated with surfaces. Jeff?
So on that homogeneous equation, instead of using delta HF, you use delta
Let's go back and look at this. I'm trying to remember. No, I think it's it's the same, because delta GV we defined it above. I didn't notice I made that. All it is delta GV, we defined it up here. You can write, if you've got delta GV, this thing, you can turn that into delta HF, basically. So I've skipped that step on the heterogeneous step. I haven't noticed that until now. I'll go back and correct that for next year.
So, but we don't need to convert those two delta G delta H.
No, just use these formulas right here. That's all I need to know for this exam. And you could use it, but you don't need to. Should we do last question on this, or should we move on to N star? You have a question on this, Arthur, or something else? Okay, let's do N star real quick. Okay, so I think we got a good handle on R star and delta G star, the activation energy and the critical size. So what is N star? That's the number of critical nuclei at any given temperature, right? At any given temperature, oh gosh, turn my phone off. Sorry, just silence this. All right. So N star, that's the number of critical nuclei that exist at any given temperature. What should it look like? It should look like this. If this is, say, temperature, and there's your temperature when you have the solidification that you expect it to occur at, that's T alpha beta. Down here, plotting this would be N star. So the further and further you get below the temperature where you expect it to transform, the activation energy gets smaller and smaller, so you should see more and more of these things, right? So this curve should look something like that. It should take off the lower you go, right? The number of these critical nuclei. The expression for that is like this. It's N star equals K1, where this is just a constant, multiplied by the exponential of negative delta G star, divided by, is it 1 or 2? Let me pull this up to be sure. Just 1, kBt. Boltzmann constant times temperature, just like so, right? K1, what is K1? K1 in the book, they say that K1 is equal to, is the number of atoms, or if we're talking about molecules, it'd be the number of molecules per unit volume, right? So since we want N to be a number per unit volume, this thing has to have the same units because exponentials have no units, right? So this has to be number of something per some volume, right? And what we do is we just start and we say, all right, let's assume that out of all the atoms that are there, some fraction of them will be clumped together to form these nuclei. So you start out figuring out how many atoms there are per unit volume, which you could do using the density, right? And the molecular weight of whatever it is I give you. And then you're going to multiply that by some term that reduces that between 0 and 1, right? And the bigger the activation energy, then it's a big reduction. If it's a small activation energy, then it's not a big reduction. You're going to have lots of nuclei. Any questions on this? I can't remember who asked it. Rosa?
So it goes, you get more nuclei when the temperature is lower, but why is that? Because if there was less heat, wouldn't that mean there was less energy? Or
Good question. This is basically, first off, we assume that all these atoms are sort of randomly vibrating and bouncing around each other. It's a liquid. That's a pretty fair assumption. And at any given time, they randomly bounce together in something that looks like a crystal. The crystal looks at itself and says, am I bigger than my critical nuclei size? If it's bigger than it, it says, great, I'm going to keep on growing. If it's smaller than it says, nope, and it's going to redissolve again, right? So your question is, why does that process get better and better as we go down to lower and lower temperatures? Because you'd think thermal motion. So you're right. You're absolutely right. The way to explain it is the fact right here. Actually, we talked about it right here. So in the notes, if you go back to here, you'd expect this to be this looks like a thermally activated process. This looks like something that doesn't get bigger as temperature goes down. You'd expect it to get bigger as temperature goes up, except that delta G star is our activation energy, and it's not constant. In other processes like diffusion or creep or the many things we've talked about in this class that look like this equation, that numerator is usually a constant that's not changing. Here, that thing definitely changes with respect to temperature. We know how it changes with respect to temperature. It changes like this. Right here, right? Temperature is in the denominator squared right there. So your activation energy changes. So you're right. You'd normally expect that to get better with higher temperatures, but in this case, the activation energy really shrinks at lower temperatures, and that causes you to actually go the other way. Other questions? Yeah, Thomas?
The constant KB.
Constant KB, that's the Boltzmann constant. You can just look it up. That's something for the note sheet for sure. Boltzmann constant. I usually like it in EV because we're talking about things like atomic processes, and their energy is it's on an EV basis rather than a kilojoule basis. So this is something just to write down. 8.617 e to the negative 5 EV per K. I usually would provide something like that on the test, but I think you should write that down on your note sheet. And again, you could also ask for it in joules, right? But it's more commonly in this class going to be used in EV, and we'll do the gas constant in joules. Okay, other questions? Yeah, Arthur? Anything else on this? Number of critical nuclei? Let's keep going. What else?
In the energy band gap window relationship right under it, that's just for that's just for one atom, right?
Well, no, it's for a semiconductor, right? So when we say a band gap energy relationship, first off, we're going to pick a material that has a band gap. Let's start with like silicon. Silicon has its Fermi level is in the middle of a band. So it's a semiconductor. It's not an insulator or a metal because the band gap's not huge. If the band gap was huge, it would be an insulator, but it's not. It's something like 1.1 electron volts, I think, for silicon. So these are all occupied states, and these are empty up here, right? The conduction band is empty. The valence band is full. So what happens if we promote an electron to that conduction band, thermally, with a photon, whatever, right? You hop an electron up here. So now I've got an electron and you've got a hole. If you don't do anything to separate those, like a solar cell does, it causes the electron to go this way, the hole to go that way, and creates a current. If you don't do that via p-n junction, then after some period of time, it's going to what we call relax. It goes from its high energy state, and it's going to relax back down to its low energy state, right? So it will actually relax and go back down to the spot where it was before. But since energy has to be conserved, when it does so, it's going to give off light, right? You're going to give off Hc, right? Energy equals Hc over lambda. So you're going to give off a photon that has a very specific wavelength. So let's do this real quick. We're going to calculate what would be the wavelength of light if you made an LED out of silicon itself and didn't dope it in any way. you're relying on electrons dropping down from the conduction band to the valence band, what color of light would this produce? Let's do that real quick. It's 1.1 electron volts is our total energy, right? 1.1 electron volts. We're going to set that equal to H times C divided by lambda. So we want to solve for lambda, and once we know lambda, you'd use a table basically that says what color that is. I will provide a table for color on the test, right? So let's look up what Hc is. That's Planck's constant and the speed of light. So let's do Planck constant. Let's do it in electron volts. Since on the left-hand side of our equation we have something in electron volts, let's make those cancel out. So Planck's constant right here in electron volt seconds is 4.136 e to the negative 15. So let's write that down. So 1.1 eV is going to be equal to 4.136 times 10 to the negative 15 eV per second. That's multiplied by 3 e to the 8 meters per second. So our seconds cancel out. Electron volts cancel out, and therefore when we solve for this, when we bring this wavelength over and 1.1 over, that answer is going to be in meters, right? So let's do that quick. So tell me what you guys get on that. Yeah, Connor?
So when we're making our solutions, how do we know which units to write down all the constants that we do?
You can write down how to convert between units is the easiest answer. If you don't know whether you want it in electron volts or joules, figure out that in 1 joule it's 1.60 to 19 electron volts. Yeah, or just write them both down. And again, I usually give you units on tests. I try and be good about that. Constants like that. Yeah, Haley? Yeah, if you punch it in, I get 1.128, right, microns. So 1.128 times 10 to the negative 6 meters. That means that our wavelength is 1.128 micrometers. What color is that is the next question, right? So first off, color is normally thought of in nanometers. When you talk about color, like green is like 300 or 550. I'm drawing a blank. 550. So it's usually nanometers. So let's convert this to nanometers because the table that we pull up, the picture is going to show it in nanometers. To do that, nanometers, there's 1,000 of those per micrometer, so we can just say that this is equal to 1128 nanometers, right? So now we just pull up, and again, this is something I'd give you on the exam. We'll do EM spectrum wavelengths. Pull up something like this. Okay. And this tells us that visible light goes between roughly 400 and maybe 800 or 750. That's stuff that our eyes, the photons that hit our eyeballs, we can actually turn that into a color and our brain can do something with it. Stuff that's less than that or over in that, our eyeballs can't even register it, right? It can damage your eyes, right? X-rays have like way shorter wavelength and they can damage your eyeballs for sure, but your brain can't turn it into an image, right? Because we evolved to only see this little tiny spectrum, right? Which is kind of weird that it chose that tiny little spectrum. That's where we're at. So this stuff, an LED made out of silicon, it is clear out over here at like 1,000, far this way, right? So that would be a really bad LED for human beings because we wouldn't be able to see any of the light that it's giving off, right? It is giving light off. In fact, you can make an infrared laser out of silicon, right? A laser is basically you take all these photons that this band, this collapsing from the conduction band down to the valence band, that gives off a photon. If you give enough of those and you collect them together and put them in the same phase with one another, point them all the same direction, that's all a laser is, right? So you can make an infrared laser out of this thing, but we couldn't see it. Something that's interesting, birds can see in the infrared. If I had a sheet of silicon here, a bird could see right through it because their eyeballs evolved to see infrared. You guys are impressed. That is super cool, I think. All right, Rosa.
I'm just curious. How come, like, if we have a laser, you shine it on the wall, you can see it on the wall, but you can't see, like... the beam.
Can't see the beam, but it goes through all. So what we're seeing is the reflection of the laser, right? When I take a laser pointer and I point it at the wall, that light hits the wall and it undergoes what's called diffuse scattering. Specular reflection is when it's like a mirror, like X-ray diffraction is specular. The light came in at this angle, it left at that same angle. Most things don't specularly reflect particularly well. Like this wall, it has some roughness, so when the light hits it, it's going to actually diffusely scatter in lots of directions, and we're seeing the reflection. In air, there's nothing for it to reflect off of. Okay, other questions, Rob?
Is there a way for you to like induce this like regularly, like for you to produce these?
Take 3210, MSc 3210. You'll learn all about inducing this regularly to make lasers and pumps and all sorts of cool things. But we're not going to cover it in this class. Great question though. Jaren?
Is there a way to like solve for the energy bandgap?
In this class, there is a way. We didn't get to it in this class, so you're not going to be expected to in this class. Yeah, there are ways for sure though to predict the band gap. Actually, I guess we did talk about one way to do it. Let me briefly say this. In this class, we did briefly give you one tool. It's not on the exam, so I'm not going to spend a lot of time on it. But if you were to calculate, let me just go and I'll show you it. From carrier concentration versus temperature plot, you can get it. It's right back here. Right here. If you take so you don't dope it, you take an intrinsic material that's undoped, you heat it up and you monitor with something like the Hall measurement what the carrier concentration is, the slope of this will tell you the band gap. Because the slope of this, if you plot this a log plot up here, right, versus 1000 over t, that's your slope. You could get your band gap out of that. That's the only thing we've talked about in this class to do it though. Arthur?
So if ever we have a problem that uses a constant and we have an EV, you're not going to give us a constant joule and then expect us to convert that.
You could. I mean, so again, joule to EV is an easy conversion. You just use the fundamental charge, right? Let's say other way around, EV to joule. I think that's 1 over the fundamental charge. Yeah. Electron volt to joule is just fundamental charge number of them. If you take 1.6 e to the negative 19 of those things, a joule is 1 electron volt is fundamental charge times a joule. So if you wanted to, you could just write that down, or write them down in both. That's fine by me too. Other questions? Or better yet, get a calculator that does it for you. Make your lives easier. That's my suggestion. But Haley? Yeah, let's talk about phase diagrams. Anything else on, let's move on. Let's find phase diagrams. Okay, right here. All right, phase diagrams. What's useful to review here? Lever rule, reactions, what's useful? Yeah, Rob?
One last thing about the last.
Oh, yeah.
That equation that you showed for you said it was one of the ways that we could use to derive a band gap. What was that equation?
It's not on the final, so don't sweat it. It's in the notes in chapter 12. We want to go back and look at it. Okay, so phase diagrams. We've talked a lot about these in this class. The reason we like them so much is they help us know from a thermodynamic standpoint what phases should exist under different conditions. So we'll go back to like our most simple binary eutectic. We've seen this to death, right? It might look something like this. In this binary eutectic, when you go from pure component A to pure component B, there is solid solubility over here. Solid solubility, meaning we can dissolve some of atom B into this pure atom A, but there's no solid solubility on the other side, right? The reason why you expect to see solid solubility is if the atoms are similar to one another, right? When you see asymmetry like this, what that normally means is there's a big size difference. So if you've got a really big lattice over here, like let's say this A is a really big atom like lead, then you've got a much smaller atom over here. Well, you can take out a really big lead atom and substitute in a smaller B atom, right? But it's harder to go the other way. If this is a small lattice over here, like boron, for example, that's a small atom. It'd be hard to pull one of those out and stuff in a gigantic lead. So instead of doing that, it's just going to precipitate out a new phase, right? Now you've got a mixture of two phases. Your lead atoms, rather than substituting for boron, they're going to clump together and you're going to form, depending on what temperature, you're going to form some compositional solid solution of mostly A. Okay? When you label these things, the trick is always to start at the top and move down. Find where the liquid is. Be sure it's liquid, right? Start going down. So you've got, just invent any name you want for these. Alpha plus L. Actually, don't do any name you want, because I think someone on the last test did like smiley faces. and like frowny faces. Oh, okay. All right, I'm making him grade that one then. Beta plus L, this would then be alpha plus beta, and this thing right on that border would be beta. That would be a line compound on that far border. Okay? At any given point here, we can do the lever rule. I'm going to just briefly recap this. At any point, let's say this is the temperature we care about, right there, T1. If we're at that temperature, you can then tell me a composition. Let's say we're at this composition. And we could use the lever rule to tell you exactly how much of each phase is present. Now, if this is plotted in atomic percent B, then when we use the lever rule, what we're going to spit out is atomic percent of alpha and beta, right? And again, the way that you do this is by drawing these regions, right? So this region right here, that's one region. That region is another, and then you've got the total distance, right? From those things, you can do the lever rule. I think it's easier just to give these names. So we'll call that roughly 100. Let's call that, say, 80, and give this thing like 20. So if you wanted to know the atomic percent of the alpha phase at temperature T1, it would be equal to what? The alpha phase, what do we do? That would be 100 minus 80 over 100 minus 20, right? So that's 20 over 80, that's 1/4. It'd be a quarter, right? And looking at it, that's right. The line is closer to beta, so it should be mostly beta. It's actually 3/4 of the way towards beta, so it should be 3/4 beta and 1/4 alpha. So it consistently, graphically makes sense. Anything else I can answer on this? Arthur? For the amount of beta? Yeah, let's write it. Sorry, one more time? So this is the lever rule. We could also do the lever rule to figure out the atomic percent of beta at temperature T1. It would be equal to 80 minus 20 over 100 minus 20, which is just, so if this one was 25%, am I doing that right? Yeah, 25%. This one would be 75%. Okay? Takara?
Well, we need to know how to draw microstructures.
Yeah, you do need to know how to draw microstructures. So again, the way to do that is typically going from high down to low. I think that's what we do on this exam as well. But you basically say, all right, if this is our composition right there, as you go about cooling it, you could use the lever rule as many times as you wanted to. I'm not going to make you do this at many temperatures. I'll probably have you draw like 1 or 2 at most. But you'd say, okay, just above the eutectic temperature, what does a microstructure look like? And you'd say that's easy enough to do. It looks like, you could do the lever rule, but it's about a 50-50 mixture, right? Because you're going between that point, this point, and that point. These should be touching, right? Right? So that's about a 50-50 mixture. So you'd say there's 50 volume percent globs of the beta phase floating in liquid. You could tell me that the liquid has this composition. It has the eutectic composition, right? Whereas beta phase is basically pure B. If you were then down here and I said draw the microstructure, well, it's no longer 25-75. It's probably like 20-80%. But still, you will have some pro-eutectic phase. You'll have some pro-eutectic beta, right? Everywhere else is going to be lamellar structure, mixture of alpha and beta, right? And you would label the compositions, the amounts using the lever rule. Conrad?
So as far as kind of looking like homework problem number 6, do we have to be able to figure out detectors and stuff from isothermal graph as well? Or is that something
that's fair game. I didn't put that on the exam though.
Okay.
Yeah, but that would have been fair game. Yeah. Remind me your name. Landon.
Can you go over real quick detective, paratactical, and effective?
Sure. Yeah, let's jump over to. So let's just go to a weird one at the end where we can see a couple of these things. Let's take on this one, right? This diagram, it's probably got a couple of these things, not all of them. What does this have? What do you guys see? It's clearly got some eutectics. That's a eutectic. That's a eutectic. What else does it have? It's got line compounds. These things, 1, 2, 3 line compounds. Technically, the end members are line compounds, but you don't usually label them as such. What else? Anything else interesting? So remember, a eutectic. My lines disappeared. It's weird. And then those disappeared. It's odd. Right? A eutectic is when you go from a liquid to two different solids. This is odd. All right. Then a paratectic is when you go from a liquid plus a solid to a new solid. Right? Do you see any of those? Yeah, the line compounds at the top of them, right here. That's really weird. This thing's gonna like freeze on me. So just above that, you've got a mixture of this line compound, the KMgCl3 and liquid. But if you go down in temperature, you now have just K3Mg2Cl7, right? So that is liquid plus alpha going to beta. So that's your paratectic. You got another one right here. I think that this is just funny labeling. Actually, no. If you zoom in, I think this is another eutectic. This is a congruent melting point. That's a congruent melting point. I think that's what's going on there. You need to zoom in to see though. Okay, Arthur.
So, similar to the homework, how could we find? We saw before we have to label the crystal structure, but how can we find the group chemical formula?
Good question. If the plot is given in mole or atomic percent, which is the same thing, then it's really easy, right? In this plot, how did you know that the formula is this? Well, first off, they're going between pure KCl on this side. That is bizarre. Something funny happening with this. Maybe it's kind of, I'm zoomed in from it. Let's change that. All right. You're going between pure KCl and MgCl2. Nope. MgCl2, right? So if there was equal amounts of those, a 50-50 mixture right here in the middle, you're literally just going to add those two formulas together. One part of this, one part of that. So you'd say that that should be 1 KCl, 1 Mg, and then 3 Cls. And that's what the formula is there. KMgCl3. If it's something else, like let's say it's at 1/3 of the way across, that means that for every one of these, for every for every one of these, you have 2 of those, right? If it's here at 0.4, that's a weird refraction. Do it out of 5. That means that 2 out of your 5 are this, 3 out of 5 are that, right? And that's how you put together those formulas. If you don't know how to do that, what you can also do is, that's the way to do it. You divide them and take a ratio until you get an integer.
Okay. And if we get something that's in mole percent, are we going to get questions that are related to mole percent? Or would we also questions that have mass percent?
We could also go to mass percent. How do you do that? Let's say that I give you this plot and I say, here's this point temperature, here's this composition. That is just bizarre. Anyways, I want you to do the lever rule at that point, but then I say, it's gone. Anyways, if I'm asking for it right, oh yeah, it's upset. We got this conflicted copy going on. All right, hope that didn't end the world. Okay, if you are right here, and I'm asking you to do the lever rule, when you do the lever rule, that's going to come out in mole fraction of the whatever 2 phases are in this field. If I ask a question, I say how many grams of each are there, what's the weight fraction, then you're going to have to use the molecular weight of these 2 phases and convert moles to mass and then take mass fraction, right? So if you don't remember how to do that, well, first that's not on the final, but you could do that. We did learn that in this class. But if you want to study it, then you'll be fine on the final. What's your name in the blue shirt? Matthew.
Can you go over heat treating alloys into this diagram?
Okay, so let's say that you're right here in this diagram, right? Let's say that you start out and you're right here. What will happen if you heat this thing up? Bizarre. Can you hold that thought? So if we heat this thing up, all of it goes to beta, right? If we slowly cool it down along that same line afterwards, once it's all turned into beta, what will happen as you first cross that line? You're going to start to, that's so weird. You're going to start to form a little bit of your alpha phase, right? Where will those likely precipitate? Good question. We didn't talk a ton about this in class, but grain boundaries would be the right answer for what we said. That said, we didn't have time to get to it in great deal in this class, but if you're at low temperatures when this happens, like down here, like this is not like a very high temperature. So if you're not at a high temperature, then what's going to happen is that you don't have the temperature and the time necessary for these things to migrate all the way to the grain boundaries. So instead what happens, like imagine like if this is the grain, like this big middle section of students is the grain, and you cool it down to a temperature where all of a sudden Kyle and Warren want to get out, right? And they would love to get all the way to the grain boundary, but because they don't have enough thermal energy, they're going to form a tiny little precipitate in the middle of this big grain. So this is actually, we didn't quite get this in chapter 11, we had to end before the very end of chapter 11. This is called precipitate hardening, right? And on alloys, if you do this low temperature anneal, and you choose a temperature where you specifically cross one of these phase boundary lines, it won't segregate all the way to the grain boundaries, which maybe doesn't give you the hardening you want. What you want instead is a bunch of tiny little precipitates all through your grain, because every one of those little precipitates will pin your dislocations. If you pin your dislocations, you chose harder and stronger. So that's a common heat treating they'll do to aluminum. Like lithium, they'll do that with lithium and aluminum alloys. The lithium will precipitate out little tiny precipitates. They'll do it with copper alloys. It's a way of strengthening it. Okay? We've talked about steel, though. If we go back to Kinetics chapter on steel, we certainly showed a bunch of these things that in steel, we have more than just the phase diagram to help us. We have TTT diagrams where somebody has quantitatively actually plotted the kinetics of different reactions. Let's go to one like this. Let's go to one like this. This is just for eutectoid steel, where basically, from a thermodynamic standpoint, as soon as you go below this eutectoid temperature, it should want to form alpha and cementite. But in practice, it depends on how far you are below that and how long you hold it there, what sort of microstructures you actually achieve. If you do it in this region, sort of above the nose, this whole thing sort of is called perlite. The bottom end would be fine, the top end would be coarse. Out here should be spheroidite. It's not drawn there, right? And then if you do it below the nose, you form bainite. The only difference between bainite and perlite is the thickness of these lamella that form. If they're really thick, coarse, we call that perlite. The reason they call it is because like mother of pearl, you can kind of see like this striping nature in it. Bainite is really fine. I don't have a good way to memorize that. Arthur. Why is there a nose? Yeah, we can't explain that. It goes back to the earlier part of this chapter in kinetics when we said that transformation depends on a couple things. It depends on the nucleation rate and your diffusion rate. Those two things together give you transformation. Right? It's not enough just to nucleate things. Those have to grow. Your phase has to nucleate and then grow. Nucleation occurs at one maximum value because it's competing with number of critical nuclei that takes off and diffusion, whereas this thing just competes with diffusion up there, right? So those two things convoluted together gives you your total rate of transformation, okay? Again, maximum rate corresponds to a minimum time, so that's why you get this nose in the TTT diagram. Yeah?
And I just touched on this, but just to clarify, when do you tend to get a lamellar structure as opposed to like precipitate pockets?
Lamellar occurs when you're forcing a reaction to go from a liquid to two different solids, or from one solid to two different solids at a single temperature. Basically, if you make it happen fast, then they're not able to segregate out and form big grains with less surface area than these little zebra stripe things. But if it has to happen fast, it has to happen fast, and that's what leads to this lamellar structure. So eutectoid temperatures and eutectic temperatures, where you see those. Yeah. We're out of time. If you have other questions that I wasn't able to get to in class today, there's the review session from 5 to 7 tomorrow. I will also be in Monday after like 11 all day if you have final questions. And tomorrow I'll be in the morning, so swing by my office if you have questions and I can describe it. And then one last thing is thanks for an awesome class. Thanks for putting up with a bunch of silly demos and making you guys into atoms. I appreciate it, and I love teaching this class.